So today we are going to talk about compatible observables, and we'll be proving one theorem, which is, suppose that two observables A and B are compatible observables and eigenvalues of A are non-degenerate, then the matrix elements of this kind are always diagonal. So first thing we'll try to know is about this. What do we mean by compatible observables? So that is these brackets are called commutators. And what happens in that? Multiply this first A with B, do the minus, which is 0. So for compatible observables, commutator of A and B is 0. Why do we generally use this? So we have seen that operators can be represented as matrices, and this property is very often seen in matrix multiplication. If A is an operator represented by some matrix, B is some operator, then matrix multiplications do not commute. So for matrices, not necessary that some degeneracy. What do we mean by that? Say, suppose there are two or more linearly independent eigengets of vector A. Say since these are eigengets of operator A, then what can happen? When I operate operator A, it's eigenget, in return I get some eigenvalue, and the same vector eigenget again. Let's say taking another eigenget, but this time I am coming back with the same eigenvalue. Let's say extending this, again I am getting back the same eigenvalue. So each time this operator is operating on the state or eigenget and getting back the same eigenvectors, but multiplied with some eigenvalue, as we know from the standard eigenvalue equation. But now again I am operating on some different state, which is again eigenget, but I am not getting back, let's say a double prime or some other value, but I'm getting like the same value. So these all states are called degenerate states, and their eigenvalues are degenerate. Here there are three such states. Then I can say that eigenvalue is threefold degenerate. It's threefold degenerates. So there are three different states, but they all have the same eigenvalue. Let's get to the proof of this. Let me write. We just learned this is collected A minus B. A can operate on this, gives some eigenvalue A double prime. A can operate on this, gives some eigenvalue. Prime minus B prime. But we know that for compatible observables, this is 0. We are saying that A and B are compatible because we just quoted that this is going to be 0. So this will be 0. Also, since we just quoted that this is non-degenerate, eigenvalues of A are non-degenerate, that means they are not same. So this can get cancelled out. The remaining part is this one. This is 0. Since this is going to be 0, one more thing. Suppose if I write it like this, there is a function which is multiplied so if A prime and A double prime are same, this will be 1. I will get here these elements. If not, which is our case, if A prime is not as same as A double prime, which is the case of non-degenerate, this will be 0, which we are getting here. So the only case when equation 2 is not 0 diagonal. How do we write a matrix element, which are diagonal elements? Write it like this. A prime, all possible cases. So this is the proof that the matrix element like this are supposed to be diagonal. All other elements, all the non-diagonal elements are zero. Only the case where this is same, this is coming out to be non-zero. So what we notice in this is that when two observables A and B, they are compatible observables and A has the non-degenerate eigenvalues, then operator A and B observables are commuting and are non-degenerate eigenvalues, they share the eigengates. I can represent them with either of them and it's still fine. So if I know eigengates of one operator, I can represent another operator with the same eigengates. Let us notice something different here also. I can exploit the identity here. This will be zero of diagonal elements, so I can rewrite this same condition using Kronecker delta. The two sums, this will give one sum, provided this constraint is implemented. A prime is seen as a lower prime. So either of this one. Let's try to operate this on a eigenvector A. This will give a this Kronecker delta will give this sum and make all of them, let's say, A prime. So this will 1. I will be left with this multiplied with this. Operating this operator B, the eigencat of A, let's say A prime, I'm getting the same A prime here multiplied by this diagonal elements of matrix B. So just some number. Right. So we say is this A primes are eigencats of operator A. It turns out that B is also the same time, at the same time can be operate on A prime and give me the same vector. So what we can say is this, that A primes are eigencats of A. It turns out that B can also operate on A prime and give the same eigenvalue equation. So B primes are called simultaneous eigencats of A and B, provided that they are compatible with each other. How do we denote the simultaneous eigencats? Sometimes the collective index is also used. Suppose we now extend our argument to more than two mutually compatible observables. found, let's say, maximum number of commuting observables set of. So also So what we are trying to see here is we will reach an interesting result that if we have a maximum set of compatible observables, all mutually compatible with each other, and the operators or the observables have eigenvalues which are, let's say, have some sort of degeneration 2-fold or 3-fold or 4-fold, let's say anything, then since there are degeneracies, since we expect that there are no, since there are degeneracies, there will be many states which will share the same eigenvalue. But here, if there is a state, combined state, a simultaneous eigencat or simultaneous eigenstate, combined with very specific state, then this will turn out to be unique state. So for that we have some arbitrary state alpha, now that we make a measurement of A, and we obtain some value given. How can we write this? A alpha give me A prime state. Let's say I have a state like this. You can say this. Right now I'm keeping only 2, not 3 terms, only 2 terms. Then I perform a measurement of its operator B on this state. Here the value was A prime. Here B prime. Keep in mind that this is a unique state. Since I have specified both these things, this is a unique state. Again, I'm making a measurement this state, and with certainty I'll get this back. Because the state is uniquely specified and its eigenvalues are non-degenerate. That's how we always started. So this part will be certain. I'll be sure that I will get this value. Now suppose there is degeneration. Let's say in this state there is degeneration. So when we make a first measurement, then what will happen? The state will not be unique. So after first measurement, what we get is so this is not a unique state. This represents n-fold degeneration. So there will be n such states, all having some probability represented by this. So a1, a prime b1, a prime b2, a1 b1, a2 b2, a2 b2. So there are multiple states, not unique state. What we had here, unique state. But here, because of degeneracy and the state B, there will be multiple states available. Suppose of this linear combination, there will be multiple states, and if I measure with operator B will select anyone, then let's say so this state is selected by operator B. There were many states, operator B took any one out of again third measurement is performed. On this state, again I am measuring, I'm doing the third measurement with this operator A. This is again simultaneous eigenvalue of operator A and B. I am measuring A, which will give me A prime with certain right. So here also I was getting A prime with certainty because this state is simultaneous eigenstate of A and B. Here also we introduce degeneracy in one of the states. Still in the third measurement I am getting A prime with certainty. So it does not matter whether there is degeneracy or no degeneracy, you get A prime eigenvalue with certainty. So observables, if are compatible with each other, their measurements do not interfere with each other. Right, so this is what we learned, and we learned that if observables A and B are compatible with each other, that means their commutator is 0. That means that matrix element of B is completely diagonal, only the diagonal elements will survive. We also learned that this operator B can be expressed in the eigencats of A, so they share eigencats, is A and B, if they are compatible. We also learned that how we can represent simultaneous eigencats with a different notation, but using specific combinations of A prime and B prime, this can be uniquely specified. Also, it does not matter that whether there is degeneracy or not. If eigengates, if they are compatible with each other, their eigengat measurements A and B, they do not interfere with each other. With certainty, you get A prime always in the third measurement.